Well, thanks everybody for joining us. We will be starting here in about 2 minutes. I'm just going to share this screen for a little bit more for everybody that's in right now. If they need to contact us with regard to CEUs or anything with related to the webinars and recordings, you can contact Allie Crampton at the email listed above. And the website to access our TN-POP program and to access the previous slides, they are listed below. These will also be in the chat, so it would be a little bit easier to copy and paste instead of just looking at it from the screen. I will turn this off before we begin, so I just want to make sure everybody had this information. All right, everybody, I think we're going to start this next webinar. So good morning, and thank you, everybody, for joining. Welcome to the Optimizing Biological Nutrient Removal in Tennessee Wastewater Treatment Plants webinar series. This is the 4th webinar of the series. My name is Mark Valencia, and I will be hosting your event today. We have 3 more webinars left for this series, so we're almost getting to the end of these awesome webinar series, and I thank Grant for helping us out with this and teaching us a lot with regard to plant optimization and nutrients. A few things first. Please notice that you have been muted upon entry. This is to help reduce any background noise, but you can unmute yourself and ask questions if you like to. Grant loves to get questions throughout, so feel free to jump in if you have any questions, but we'll also be checking the chat feature as well. Another way to ask a question is through the chat box. That is on the right of your screen. You'll see a little drop-down menu listed as chat. That's where you can field additional questions, and we have people looking out for those questions, and they can ask them on your behalf if you don't want to just jump in and ask a question. Please send questions to everyone or directly to the panelists, but not the presenter alone, as he will not be able to see them while in presentation mode. The panelists and I will be monitoring the chat box and the Q&A section. We will read them to the presenter at natural stopping points. Also, if you will, let's take time to check out the yes or no button. So if you go into the box to the right, under participants, you can see where there's a little hand symbol, a green symbol, and an X symbol. Throughout the presentation, we may ask some yes or no questions. So to see if you know how to use these, just click the green check as a yes. I'll be seeing if everybody could be checking those off. I'm seeing green check marks. That's awesome. So that would be an indication for a yes or no question that we may ask throughout the presentation. Just note that you got to uncheck it to turn it off. So in case we ask another question later down the road, you may already be checked as a green check or an X mark. So just please uncheck them so we can continue on and we won't have any accidental yeses or nos. Once you have clicked an answer, please also note that you will have to uncheck it. That's something I just read. Our presenter, Grant, wants everyone to know that he enjoys your engagement and prefers to be interrupted with questions. So please feel free to unmute yourself if you have a question that needs to be answered immediately. We will have 3 polls for you to answer throughout this presentation. The one in the middle will also allow you to take a quick break. You were able to get approved for 1.5 CEUs for each of these sessions for your wastewater license. For folks that are viewing this training as a group, we will need you to email the names and license numbers to Allie Crampton. And this is the email that I showed earlier. It's Allie, ALLE.Crampton, CRAMPTON, @pn.gov. We also listed her email in the chat section, so if you need it, it's listed in there. Shoot her an email after the session, and she will include you on the course roster. This session will be recorded, and we will make it available on our Tennessee Plant Optimization website, along with the previous 2 webinars. There's a couple more, I believe. Also, if you have Microsoft Teams on your computer and you feel WebEx is running slowly, closing out of Microsoft Teams helps WebEx to run more smoothly. Before we continue on with our presenter, Karina has some additional information and updates to share with y'all. And Karina will also introduce Grant. So you have it, Grant.
Thank you, Mark, and good morning, everybody. It's good to be back. My name is Karina Bynum, and I am with the Division of Water Resources here in TDEC, and I've been working with the grant on the plant optimization programs and pilots since 2014. So now I guess I'm the official coordinator for the Tennessee Plant Optimization Program. So if you have any suggestions, I'm sure you can find me. But let's welcome Mr. Grant Weaver to the 4th session of our WebEx series. Grant has been working with us since 2014, optimizing wastewater plants across our state, across Tennessee. He's a professional engineer and a licensed operator. Today, Grant will be talking about nutrient removal in oxidation ditches. We have quite a few of those across Tennessee. I hope you enjoyed the presentation. Please ask questions and send us your comments. We all appreciate your engagement, and Grant loves the interaction, and it makes it more enjoyable for everybody else. So don't be shy. Use your chat functions and question and answer function, and you can also raise your hand if you want to ask a question in person and you're not able to unmute yourself. Next to the check mark is a hand. You click that, and our folks will see it, and they'll be able to unmute you. So without further delay, Grant, I would like to hand it off to you and welcome you to the series.
I'm going to hand you presenter mode right now.
All right. Well, thank you, everyone. Now I got to go through the mechanics of figuring out how to get my screen to be the one to work. And I think if I push the right button, you'll now see this. Get that little box out of your way. All right, team, is that working? We're on, right? They're in my screen?
Good to go.
All right, let me know. We've got a lot of ground to cover today, but as Karina and Mark and Allie, I think all 3 of them said, I welcome comments, questions, interruptions. It makes it more rewarding for me, and I think it makes it more entertaining and more educational for you. So please, anytime, send the team questions and comments, and we'll stop and engage in those. I can always work my presentation around no matter how many questions there are or comments. So, as we said, this is hump day, I guess, in the presentation series. We're on the 4th one. We've done a background on nitrogen, background on phosphorus. We've done an overview, and today we're going to drill in. We're going to talk about oxidation ditches. And the last count, just as I switched over to presenter mode, I saw there were 77 people listening in. So thank you. My job here is to work for you and to give you information of value. So I'm going to give it my best. Hopefully you find this worth your hour and 3/4. And if you do, next week we have a session on SBRs. Then another session similar today for FBR, similar today for conventional and extended air wastewater treatment plants. And then the most fun of all, typically for the audience, for everybody involved, for me and everyone else, is we'll talk about some specific plants we'll brainstorm together. We'll kind of do a whiteboard session. We'll put them up, put photos of the treatment plants up there, and we'll have the operators talk to us. We'll talk to the operators, figure out what's working, what isn't working, what they'd like to see happen, and see if if we learned anything in these last many weeks that we can apply to these case studies and have some back and forth on that. That's the goal. So if you're interested, just please, in that chat box, just let us know that you're interested in possibly being one of those volunteers, and we'll talk to you some more about that. I want to do a quick review. I'm going to do a quick review of nitrogen and phosphorus, and then we'll get into the oxidation ditch. Okay? So the science, I like the ORP. Talked about oxidation reduction potential. I like it because it's a tool that measures how hard the bacteria are working to breathe oxygen. If they're breathing free oxygen, DO, it's a positive number. If there's no DO available, or if they're working to breathe the oxygen that's combined, even if the DO is available, the ORP will go into negative numbers. Dissolved oxygen, probe stops, obviously, when the dissolved oxygen is 0. The ORP tells you how anaerobic, how strongly septic the water is. Nice tool. It's got its downsides, the reproducibility. It can take a while sometimes for it to equilibrate, but I like the tool. And if you do use the tool, don't get hung up on the decimal point. In fact, I never write down the decimal points when I do readings. Plus or minus 10 is pretty much the same number. I showed this chart before. It's a chart that I nabbed from YSI. I liked it so much I've been using it for years. Let me take this chart and tell you how it applies for nitrogen. So we've got two steps to nitrogen removal. We've got ammonia conversion to nitrate. I'm going to review that in just a moment. That happens in conditions with strong oxygen, right? Lots of oxygen, highly aerobic, oxic conditions, if you like that word. And we can measure that in the ORP. We can measure it with DO, but a better measurement in my mind is ORP. I like to start with a target of positive 150, but you can see there's a huge range. The more positive it is, the stronger the ammonia to nitrate conversion process is going to be. If you get too high, you're probably wasting oxygen. So once you remove the ammonia, you really don't need any more oxygen. Also, if you get too high back over here, and you're trying to switch back and forth to a low oxygen, it takes longer to switch back and forth. So there is such a thing as too much oxygen, even in a straightforward ammonia removal. To complete the nitrogen removal process, the ammonia that gets converted to nitrate in that aerobic condition, now that nitrate needs to be removed. And as I explained before, and we'll recap here in a moment, the bacteria breathe that oxygen off. You got to stress them a little bit, create an environment that doesn't have very much oxygen, and then they'll find it in their interest to stay alive by breathing that oxygen that's bound on the nitrate. So that's the nitrogen and the ORP tool that I like to see. For phosphorus, even more valuable tool perhaps, because the first two steps of phosphorus removal, where we need to create the food source, the volatile fatty acids, and then the bacteria that are in with the mixed liquor that feed on that, which ultimately will remove phosphorus, they also need to feed on that in also septic conditions. The target that I like to start with there is minus 200. And when I say these numbers, they're always subject to change based on your conditions. It's a good place to start. And then as you get a better understanding, a better control, you can refine those numbers for your facility. Minus 250 might be a better number for you. Minus 300, minus 125, probably not as low as minus 125, probably more negative than that. So there's one condition, septic condition, just short of creating ammonia, just creating methane gas. So you're almost fully anaerobically digesting, just short of creating methane gas. Then those energized bacteria need to move into a totally different environment, very strong in dissolved oxygen, pretty similar to the ammonia-removing bacteria. So if you have an aerobic environment that is removing ammonia, you've got enough dissolved oxygen, you've got enough ORP, you've got an aerobic enough environment to remove phosphorus. The difference is the phosphorus-removing bacteria are more sensitive to pH, so it's theoretically possible to have a pH, say, of 6.7, something like that, 6.6, good enough to support ammonia removal, but not good enough for phosphorus removal. Otherwise, the conditions that would support ammonia removal generally will support that last step of phosphorus removal. If there's any questions or comments on that, we'll take a swipe at them. Otherwise, I'll keep going.
None in the chat, Grant.
Okay. Whoa. All right. We already have our first polling question. So I think, Mark, this is back to you. You'll take it from here, and I'll climb up for a second.
All right. Let me pull up this poll for you. One moment. All right. Our first poll is up. So on a scale of 1 to 5, how much do you know about nutrient removal and oxidation ditches, with 5 being an expert and 1 being new to the topic? So we'll let this poll run for a little bit, and then we'll close it out and get the results so Grant can see them. We have a little more activity, so I'll just give it about 30 more seconds, and I'll close the poll out. Alrighty, I'm going to close the poll out. And I will share the poll results. You see those, Grant?
I do. It looks like we have, oops, I just lost it. Oh, there it came back. So, what, about a third of the, maybe more than a third are in the middle. And we have a few people that are claiming. What is 1 and 2 now? Were those high-level knowledge or low-level?
Five is an expert and 1 is a novice.
Okay, all right. So we have a few novices and 0 experts. Come on, we can do better than that. We'll get some experts there. All right, so I need to share my screen. It's been given back to me, correct? All right, I'm back. Oh, there I am. Now I'm back. That's all me, folks. I apologize for my lack of skills. All right, well, I think you're being too humble. I think there's some people that know pretty well about nutrient removal, and hopefully you'll be even more confident in your knowledge. The nice thing with an organization like TDEC is there's people that support you. So if you have questions or comments as you're working on nutrient optimization, you can always reach out to me, and my email address will pop up periodically, or to people in your regional offices, or check right into Karina. She'll get you in touch with the right person. So let's continue our review here. Let's do a little nitrogen overview. So nitrogen, we have two environments, right, for nitrogen removal. Now, technically, wastewater, much of it is organic nitrogen when it goes into the sewers, but through some I can't climb out of that hole. Some mysterious process, the organic nitrogen is the vast majority of it's converted to ammonia nitrogen. And that which isn't, that remains as organic nitrogen, we don't have a lot of tools readily available, so we live with it. So I skip that, and we start with ammonia. That's something that as operators we have process control ability to deal with. As you can see, we need an oxygen-rich environment. But not only do we not need BOD, the vast majority of ammonia removal occurs after the vast majority of BOD removal is already done. So if you have a long, skinny aeration tank, the ammonia would remain at the influent concentration until partway through the tank when the BOD starts to decline and then the ammonia removal starts to go away. Okay, ammonia removal then is a great tool in that if you're removing ammonia, by default, you're removing BOD. So if at some point in that long, skinny tank, if that was your situation, you find ammonia is dropping down to a non-detect number, from that point to the end of the tank, whatever air you're putting in that tank is just bubbling through the tank. You're really done with your treatment. The textbooks tell you how sensitive ammonia-removing bacteria are to pH and temperature, but I'll tell you treatment plants a lot further north than Tennessee are getting year-round ammonia removal. So they're doing fine in cooler weather. The problem is if you lose ammonia removal this time of year, it's very hard to get it back until the water starts warming up. So that's always a risk if you're tinkering with the second step and this is probably not the best time of year to start. It's best to start in a couple months from now when the water warms up a bit. pH is very critical, but pH down to about 6.5 typically is good enough. So if it's more acidic than 6.5, that's where ammonia removal becomes a problem. The second step, not as pH sensitive, so if you have enough pH, enough alkalinity for the ammonia removal, you're fine for nitrate removal, but otherwise the bacteria need pretty much the opposite environment of the ammonia removing bacteria. Instead of an oxygen rich, they need an oxygen poor. You need oxygen poor because you're trying to stress the bacteria with a shortage of free oxygen, so they will work hard enough to breathe that oxygen off that NO3 there in step 2. They need BOD for that to grow, for them to grow and multiply and to have the energy to breathe that oxygen off. And a great thing there is as they exert that energy and use that BOD, you're getting free BOD reduction. You've already paid for the oxygen to remove the ammonia. Now you're getting to use some of that oxygen to break down BOD. So if you're removing ammonia, even if your permit isn't requiring total nitrogen, even if you don't foresee that coming, it's money well spent for your community because you will save the money in operation of your facility by finding a way to go to a denitrification or a nitrate removing step. So real quick, a little chemistry here is ammonia. We add oxygen. In the process, as hydrogen ions go into solution, as hydrogen ions go into solution, they make the water more acidic. So they will chew up the alkalinity. I use that analogy of the glass of ice water, where the ice cubes are my image of alkalinity, the buffer. In a glass of water, the ice cubes buffer the water from getting warm, just as alkalinity buffers our water from getting acidic. So we can measure the alkalinity and it gives us it's a precursor. It's advance warning. It's like looking at your ice cubes. As they disappear, the water's going to be getting warm soon. If the alkalinity disappears, the water's going to get more acidic. It's too acidic, and this process shuts down. So we don't want that to happen. So that's step one, oxygen-rich environment. This whole presentation is built around this picture. It just kills me. I love this picture. So step two is now we've got these nitrates, and we want to get nitrogen gas. We get nitrogen gas, our treatment plant's going to belch or something worse, the gas up into the atmosphere. But not to worry, the atmosphere is 3/4 nitrogen gas, so Grant likes to say that nitrogen is going back home to mama when we do this. So as I said, it actually consumes BOD, uses up BOD. You need BOD to drive this. If your influent is low in BOD, this can be the most difficult part of nitrogen removal, finding the organics to drive this chemical reaction, respiration really, of converting the nitrate to nitrogen gas. Of course, we want this to happen in a controlled location in the tank. We don't want this to happen in the bottom of our clarifier.
Hey, question, Grant?
Yeah.
Are there any additional byproducts from this conversion besides just the nitrogen gas?
Yes, I'm sure there are, because I'm sure there's some CO2 and other byproducts that occur, and breakdown of the molecules from much longer molecules to shorter molecules as the whole respiration process goes on. I got to believe there's a whole. I could probably cover this page with chemical equations that result during all of this. So short answer is yes, gobs of them. Anything else?
Not in the chat yet.
All right. The beauty of this process, it adds that dissolved oxygen, free oxygen. Another thing is, as we get into the next step, which is about to begin, the bacteria that convert nitrate to nitrogen gas will outcompete the phosphorus-removing bacteria. So we just need to have in our brains an understanding of how to control that so that we can get this food source for the phosphorus bacteria where they want. More on that in a minute. Some rule of thumbs here. Rules of thumbs? Rules of thumb. My tongue felt tangled this morning. I apologize. These are just starting places for those of you who want to get into this to try to set some targets. I need to update this for the ammonia removal. I'd probably put a positive 150 for the ORP. Mixed liquor, often it's a first step for facilities. They'll raise their mixed liquor. The more pounds of bacteria you have in your plant, just the more bacteria there are. There's two controlling factors that are limiting how much you can build up your population. One is the ability to put air in to keep them alive, and the other is your clarifier ability to keep the bacteria in the clarifier and from washing out. So those two parameters create the upper limit. But other than that, the general rule that I've seen is the higher the better. All right. There's my email address down at the bottom. So if anybody ever wants that, write it down, send me an email anytime, and I'd love to hear from you. I'm assuming you're going to jump in if there's questions or comments. Not hearing me jump in, I'm going to keep going. All right. Phosphorus. All right. We're doing a review here. Let's run through phosphorus. The whole idea with phosphorus is we're trying to convert a soluble phosphorus that will pass through a filter. We're trying to make that phosphorus into something that won't pass through the filter. We're trying to move it from the top 1/3 of that cedulometer into the bottom 2/3. And we can do that either biologically, which is what I preach, We can do it chemically, or it can be done in combination. You can do some of both. Now, if you do both, you want to make sure that you don't attempt to do your chemical treatment in advance of the biological. Otherwise, you're going to be binding up phosphorus chemically, so there won't be any biological binding of it. So you might want to polish it after the biological. Take the wastewater that leaves your aeration basin and goes to the clarifier. That's where you'd want to add your chemicals if you're trying to maximize biological to reduce the amount of chemicals you need. Either way.
We do actually have a question in the chat now.
Sure.
If a plant is unable to find more BOD in their incoming water, what would be the best source of organics and the proper place to input them into the stream?
Yeah, that's a great question. I'll tell you, there's no short answer to that. If the best way to find BOD is to manage your infiltration and inflow. Wow, okay, you can't do that with a snap of your fingers. The other way is if you have something that's taken BOD out, primary clarifiers, then you want to work around them. I don't know if I said it to this group, but one of my beliefs is that primary clarifiers are generally an evil thing for nutrient removal. And fine screening is now becoming really nice technology so that a lot of plants are being built without primary clarifiers, right? So if you have primary clarifiers, look to minimize the use of the primary clarifiers. There's some bigger plants that actually burp the solids back out of their primary clarifiers. They allow them to settle and then basically backwash them up so that they're maintain as much of the BOD that's coming in the front door. People are buying BOD as some kind of a chemical compound. Me, I'd look for a way to take some of my waste sludge and see if I couldn't get that to digest a little bit, break some of the cells down, and maybe get something that's somewhat, certainly not the most digestible, but something in the form of BOD that I could actually send back into my plant. That's where I would focus. Try to take my waste sludge and see if there's some way between aerobic and anoxic or anaerobic digestion, get those cells to bust down a little bit, and I could feed some of that back in. But I do that with caution. So, very problematic. So, if we're successful in getting the phosphorus out of solution, then it becomes part of the TSS, and our job is to remove the solids. 3 steps to phosphorus removal. And I'll tell you, this is counterintuitive when you first get into it. By that I mean, you think you should turn right and you really should turn left sometimes. And those are, I'll call them rookie mistakes, but we all make them. They're honest mistakes. And even with a lot of experience, sometimes you make those. So you got to be understanding of yourself that as you learn this, there's a pretty good learning curve. Well, the first step is create the food source. I talked about the panda bears in the National Zoo. They like to eat bamboo shoots. These bacteria are not as cute and fuzzy as panda bears, at least not to me. Maybe to somebody, but I don't know that I really want to be in close quarters with such a person. But they like to eat volatile fatty acids and not much else. So if we're going to get phosphorus removal, we've got to create volatile fatty acids. The good news is they're pretty easy to produce. They grow in septic tanks. So if you receive septage at your treatment facility, every truckload is a whole gob of volatile fatty acids coming in your front door. People are paying you to take. If you don't receive it, or if you don't receive septage on a regular basis that you can rely on it, you've got to create it in your treatment plant. It's created in septic conditions. The bio-P bugs, so-called PAOs, whoever came up with that, I don't like that person. But the phosphorus removing bacteria, they eat volatile fatty acids, and they need to eat them in septic conditions. As I mentioned in the nitrogen overview, and in more detail in the prior weeks, the bacteria that convert nitrates to nitrogen gas also like to eat volatile fatty acids, and they are meaner and nastier bacteria than the phosphorus bacteria, so they will outcompete them for those VFAs. The good news is those brutes, the nitrate-removing bacteria, they'll eat doggone near anything, so throw them some chicken fingers instead, and they would eat that instead of the VFA. So they will eat the BOD in the raw wastewater. So the trick then is to reduce the amount of nitrates with the non-specialty food, and then save the BFAs for the phosphorus-removing bacteria. We're going to talk about how oxidation ditches do that here in just a minute. And then these bacteria, once energized, they move into aerobic conditions, and they take almost all the soluble phosphorus out of solution. So a couple rules of thumb here again. How do we optimize phosphorus removal? We need to create septic enough conditions to A, create the volatile fatty acids in the same or different container. We need to introduce the bacteria that contain the phosphorus removing, we need to introduce the phosphorus removing bacteria, and they will consume a lot of BOD. They become energized as they consume the volatile fatty acids. Great process control tool. As they do so, they release soluble phosphorus in the solution. Then those energized bacteria move into aerobic conditions, or the conditions change and become aerobic, and as they do, they will suck phosphorus out of solution. That concludes the review. Any questions or comments?
I have a question, Grant.
Okay.
You mentioned that it's harder to remove ammonia in colder temperatures. It seems like it's harder to remove phosphorus in Tennessee summers. Can you kind of explain what may be a culprit in that?
Yeah, I'm glad you asked that. It's a very good observation, and the same one I've had too. But I'll tell you what I'd like to do is when I get my little schematics up here, I want to address that cold, warm weather issue. So I'm going to make myself a note, and if I forget, please remind me again. Is that okay?
Sure.
All right, let's do that. Anything else? All right, we're going to do a polling question here, but I got to give you a little background to help you out. Oh, wait, don't take it over yet.
All right.
Okay, I got to grab it. That's my fault. All right. There you go. You're on my screen now, right, everybody? I'm going to assume you are unless you say you're not.
Very good.
So I'm going to give you a little preview here because I want to find out what kind of oxidation ditch you have because, as I put this thing together, there's a lot of different technologies. So there's the orbital. If you have an orbital, it's rings inside each other, like a bullseye kind of design. If you have one of those, please say so when you're asked. Another one is an oxidation ditch that has all the bells and whistles. Has an anoxic zone, that's the kind of brown colored thing, and an anaerobic zone. Okay, so that's a ditch that's designed for both nitrogen and phosphorus. Okay, now the third kind, a ditch with just an anaerobic zone. Okay, this is designed for phosphorus removal, not necessarily for nitrogen removal. This one looks pretty much the same, but you'll see those arrows at the kind of top right and bottom right. So there's a little trap door, a little gate that allows, or channels that allow water to flow from the main body of the ditch in and out of an anoxic zone. So that's this one is designed for nitrogen. So we have the ones ditches with anaerobic zones, ditches ditches with anoxic zones. And then last one, and then we'll get into the survey, doesn't have any of that, just an oxidation ditch. So I'm curious, what kind do you have? Now, Mark, it's all you.
All right, let me open the poll up for y'all, and we'll get it going. You all should have access to the poll now, so we'll give you some time to get your answers in.
That's the wrong poll, Mark.
Is it? So that's my poll question number 2. Let me see if there... That's the only other poll I have. Because on a scale, the other one is, yeah.
All right, well, I guess we won't ask that question then. Oh, God.
Yeah, sorry, it's yeah, this one's just a poll question in regard to plant. So, yeah, I don't have it. Sorry about that, Grant.
All right, well, give it back to me and we'll keep on.
We're going to wait for this poll to close, so let's run it anyways. And for question B, you have combined SBRs and oxidation ditches. So answer B is your SBR or oxidation ditch, and then we'll see how many will be conventional sludge plants and recirculating central fish we have.
I'm going to hand it over to you, Grant.
All right. I'm not sure what to do with that answer. Of course, that answer, only 2 of you have oxidation ditches.
It's all right. We probably didn't run it long enough, but then just take over and carry on.
All right, I'm back, right? Sure. So what I want to do now is give me a hint. There's 5 different categories of ditches that I'm going to talk about. And it's just about an hour to do it. And in the ditches, I'm going to explain how and why they're designed, and then how we can make it work for us for nutrient removal. So let's start with this technology. And one of you panelists has left your mic on, I think. I'm getting a little noise in the background. Just so you know. So here's a ditch. Yeah, definitely. Somebody's got their mic on. We have a ditch with an anaerobic and an anoxic zone. So how is this ditch designed to work? In this gray or anaerobic zone, there's mixers, and the wastewater comes in and travels. There's no oxygen, and there we go. You got it. Thank you. The BOD drives the BOD, and a little bit of mixed liquor goes in here so that you create both septic enough conditions to create the volatile fatty acids, and the volatile fatty acids will be consumed by the bacteria in the return sludge and will release phosphorus coming out of this zone. So a great process control tool would be to monitor the phosphorus release from that zone. If that zone is not releasing phosphorus, if it's not anaerobic enough, then turn off the mixers. Perhaps have 2 mixers. I would start with running one of the mixers on one day for a period of 24 hours, turn that off, and run the other mixer for 24 days. And I just switch them every day. And if that isn't enough, then I'd be turning them both off for increasing lengths of time. You only need to resuspend them enough so that all of your return sludge doesn't settle out in that zone, and or so that it doesn't get so septic that it starts to digest the sludge and you're releasing too much phosphorus. All right, then from that, there's some slots in the walls, and the flow goes into the anoxic zone. The anoxic zone likewise has mixers, and as you can see, the flow with the bold arrow from the left on the bottom would flow into the main body of the ditch, and then a percentage of the flow, there's usually a gate that has a wheel and a crank and a gear on it. You can open and close this gate and control, to some extent, how much of the flow from the ditch goes back into that zone. So you're creating an environment here that is circulating ammonia-rich wastewater or nitrate-rich wastewater, where the ammonia has been converted to nitrate in the main body of the ditch, comes back into that anoxic zone and has low enough oxygen that the bacteria convert that nitrate to nitrogen gas. And then, of course, in the main body of the ditch, we're getting whatever BOD remains is being removed aerobically, and the ammonia is being removed, converted to ammonia is being converted to nitrate. So that's the design concept. These things are designed to do it all. And I was discussing it. I gave you some process control tools. You want to optimize UFA production and uptake in that anaerobic zone. And I explained some ideas on how you do that. You monitor for ORP. You're looking for a nice negative ORP. If you're not getting it, you start turning the mixers on. You're looking for a nice negative ORP down in your sludge blanket. If the wastewater is skirting over that blanket, then you're going to start trying to divert the wastewater flow down into wherever the settled sludge is. And then you can monitor the performance by seeing the phosphorus release. Is it happening in that zone? That's that gray zone. Now into the brown zone, we're converting nitrate to nitrogen gas, and same thing there. You can turn those mixers off to create more anoxic zones and monitor the conditions there. You can also open and close the gate. And the gates are typically, let's see if I can get my little tool here. Bear with this image. I think it's going to remain over to the side there for a moment. You're going to have that little bothersome grid. But right here, there's a gate that you can open and close. So if you fully open that gate, then more of this flow will go into and through this zone. You'll be bringing more nitrates in to be removed, but you potentially could be bringing so much dissolved oxygen that it could pollute this zone and reduce its ability to remove nitrates. So that's another tool. All right, get rid of that. Any questions or comments on that? We're not ready for the cold versus warm yet. We'll get to it.
None in the chat so far.
Okay, let's get a case study. This one's out of Kansas. I'm going to get rid of this banner across here, and that big thing in the middle is abandoned. So forget about that. We're talking about these two ditches down in the bottom left corner. One of them you can see is in service and one is not. The wastewater flows into this first area, and you can see it looks like a huge concrete walkway. Underneath that are three anaerobic zones. So if I get my little marker back, there's a zone in here, and then there's a wall, and there's another zone, another wall, and then the wastewater goes into the ditch here. Each of these zones has its mixers. So the flow moves through this anaerobic zone. All right, we've got somebody whose mic is on, just to let you know. She talked about a grill or something. So it goes through the anaerobic zone, then goes into an anoxic zone, and then there you can see that channel that connects the anoxic zone to the aerobic zone. The wastewater flows around that. I'll back it up. Of course, in this anoxic zone is where you get the nitrate conversion to nitrogen gas, and the ammonia removal is in the main body of the ditch, and it sends the nitrates back into this anoxic zone. Final effluent goes out to the receiving water. So for Lansing, they were having problems with phosphorus removal. So the first step is to make sure you're getting good ammonia removal, ammonia conversion to nitrate in the main body of the ditch. Then the second step is to make sure that those problematic nitrates are being removed in this anoxic zone and not flowing back into that anaerobic zone as return sludge. So we really wanted to optimize the performance here. And then once that's done, now we can try to drive this anaerobic zone more anaerobic. And Lansing's problem was, Lansing is right next to a major state prison, and there was something going on at the prison where a lot of the prisoners were being kept elsewhere while they were doing some work at the main prison. So the flows were down, the loadings were down, and they were having a difficult time getting the anaerobic zone to operate as they wanted. And the answer there was to manage their mixers. Started turning the mixers off for extended periods of time, made the conditions stronger, provided them a better environment for the phosphorus VFA production and VFA uptake, and therefore or the soluble phosphorus release in this anaerobic zone. And then of course it completes once you get the phosphorus, the first two steps in the anaerobic zone. It basically just passes through, backpedals, lollygags its way through the anoxic tank, and then finds its way into the aerobic zone, and that's where the phosphorus removal is completed. I saw a question came in, but I'll tell you, I'm not able to talk and read at the same time. So, what was that comment?
I'll jump in. What parameters such as ORP readings should operators try to maintain in the anoxic zone compared to the anaerobic zone?
All right. Getting my little tools here. Bear with me. All right. So in the anaerobic zone, I like to see a minus 200 or more negative. The more negative you get, the stronger the septic conditions, which means the greater the possibility of odors. So depending upon the chemistry of your wastewater and how near neighbors are to you, is how much you can drive that into a negative. So if you're not getting minus 200 or thereabouts, you probably need to make this zone more anaerobic. And the trick to doing that is turning down the mixing to the point of turning it off, allowing some sedimentation to occur. As it does, that settled bacteria creates an anaerobic blanket at the bottom. And then periodically, at least once a day, resuspending that material so that it doesn't sit there too long and decay. And secondly, so that you don't lose your mixed liquor, all start to settle out in here. So minus 200. The anoxic zone, I like to see that more in the minus 100. Now that's going to be constantly refreshed with high DO water coming out of that circle, out of the main ditch, coming in here, moving through. So there's always going to be a lot of DO coming in here. So this one we're going to try to get minus 100. And again, this particular tank, you can't see the mixers. They're rail-mounted mixers. So you want to cycle the mixers on and off to strengthen that low dissolved oxygen anoxic condition. So minus 100, minus 200, good starting points. All right. Anything else?
Not in the chat.
All right. So here's a ditch. That was 1 of the 5. And all right, I'm totally confused. We have another hour to go. Am I correct? No, we have another. My clock stopped. I guess the battery in my wall clock went out. I've got another 45, 50 minutes to go. It's 5 of 11 right now, or 5 of noon here in Eastern time. All right. So we're 1 out of 5 done. We'll see if we can get all 4 of the others in. Oxidation ditch with an anoxic zone. This is a pretty common design. Same as the other one, except that, right, the anaerobic zone's missing. So this is designed for nitrogen removal, but not designed for phosphorus removal, right? We don't have that anaerobic zone to create volatile fatty acids. We don't have a zone there to introduce the mixed liquor to the VFA-rich environment. Somebody's mic is on again, just so you know. How this works is in the anoxic zone, the first zone, it's high in BOD, and the nitrates are reintroduced through that channel, through that door, into that zone, but the ammonia is converted to nitrate in the main body of the ditch. So these are designed for nitrogen removal, not designed for phosphorus removal. But not to worry, we've had some success converting some of these to phosphorus removal, so if this is your type of ditch, there's a couple ways to do that. So how are we going to optimize? Plan A is to nitrify and denitrify in the main body of the ditch. So we want to take what's blue in my picture, and we want to create both an oxygen-rich and an oxygen-poor environment in that ditch. And if we do that, then we're getting all of our ammonias converted to nitrate, right, in the ditch. That's what it's designed to do. Then instead of having the nitrate converted to nitrogen gas in that brown area, if we can figure out a way to get it done in the blue area, then the brown area is now available to us. The old anoxic zone is available to us to drive it anaerobic for phosphorus removal. So let's spend a moment talking about how we would take this blue zone and make it do both, which it's not designed to do. So we got to operate the plant differently than designed, right? So if your permit says you got to operate your plant as designed, you're not going to get phosphorus removal out of it. So work with the regulator, but they're going to be cool with this idea because they're supporting this optimization effort. All right, 2 ways to do it. One is you can run it like a sequencing batch reactor. You can run it aerobic, run that mixture, that big gear right in the middle right of the blue. You can run that sucker on and then turn it off. On for a few hours, off for hours or an hour or more. Cycle it just like a sequencing batch reactor so that you have a strongly aerobic zone for ammonia removal and a strongly anoxic zone. I'm going to give you an example of a plant that's doing just that. Another option is to run that ditch so there's just enough oxygen. So let me see which way I had that gear turning. Okay, so that there's just enough oxygen in the bottom going from right to left to support ammonia removal, and most of the oxygen is depleted and sufficiently depleted so that by the time it goes to the right, the top moving left to right, that there's so little oxygen left that it will go anoxic and therefore the bacteria live, keep alive as they go through that zone and to grow, are going to breathe the nitrates off. So there's two ways. You create an oxygen-rich, oxygen-poor zone in the ditch, or you cycle it between the two. In either event, now the ditch, the blue, has taken care of your nitrogen removal, and your brown shaded is available for phosphorus removal. So now we're going to want to close that gate. This gate up here, it allows returns, or the internal recycle gate basically, allows mixed liquor from the ditch. I'm going to close that to the extent you can. And as it's closed, this then will become more septic. That doesn't do it. You start turning mixers off. Like I said before, run one day and the other day. And if that doesn't do it, turn them both off, except for periodically to resuspend materials. This then will become sufficiently anaerobic. You can create the volatile fatty acids, and you can have the bacteria that are in the return sludge that are coming in here will feed on those volatile fatty acids, and you should be able to get phosphorus removal. Let me try this next. See if we'll let me do it. No. All right, that was plan A. There's also plan B. You don't like plan B, and I don't remember if I have an example of this or not, but working with a couple plants, yeah, I do. Working with a plant that is cycling the air on and off in the main body of the ditch, and it's off long enough that not only is the ditch going anoxic for nitrogen removal, there is some sedimentation occurring in the ditch, and as the sedimentation occurs, there's a transient, comes and goes, a zone of settled sludge that becomes anaerobic, and as it's anaerobic, creates the volatile fatty acids. And the bacteria, of course, that are settling in the sludge are the same bacteria that are in the mixed liquor, so they have an opportunity to chow down on those VFAs in septic conditions. And then when the rotor kicks back on, they're resuspended. Doesn't usually dial in your phosphorus removal as well, but it's certainly an opportunity. Then plan C is to take some of the return sludge and run it through some kind of a fermenter. So you create a fat hole in the pipe, and you take, maybe you have a waste sludge holding tank, and you pump some of that waste sludge, you turn the air off on it, you let it sit in there for a few days, long enough to get ferment, to get septic, and then take some of those bacteria and send them back into the plant. If you choose to go with that option, my rule of thumb is you send about 10% back into the plant of what you waste. So if you're wasting 10,000 gallons a day, you want to return something less than 1,000 gallons a day, because that 1,000 is probably going to be a little higher concentration of bacteria. And then, of course, you're going to have to step up your wasting, because now you're bringing bacteria back into the main body. But that technique has been used. I'm going to talk about that in the Orbital system. Wow, that was a lot. Any questions or comments on that?
No, in the chat, Grant.
Okay.
Yeah, we have one in Q&A. It says, it may not be the best time for this question, but have you ever seen a massive infestation of O21N in a biological phosphorus removal plant? The phosphorus was in the range of 0.05 when the supplements got really bad. It is a plug flow firm zone followed by aerobic zone.
Wow, that's there's a lot there, and I think what I'm going to do is I'm going to punt on that question, and because I'm not an expert on filamentous bacteria, so the question really is that you're doing a great job, everything's working well, and then you get filament that takes over the plant. Frankly, I know there's a plant right now in Tennessee that I'm dealing with, that they're dealing with that very problem right now, and they've communicated the issues they're having with it. In that case, they're trying to chlorinate away the O21, and of course, in doing that, they're losing ammonia removal, creating a cloudy effluent, and they're trying to recover from that. So it can happen. What I like to say, and of course, easy for me to sit in my computer and say this, is in most cases, switching between a strongly aerobic and a strongly anaerobic, you're going to get rid of most of the filaments. But every now and then, these problems occur, and I just don't have the tools in my tool bag to help you with that problem, and I'm sorry. I think maybe I will talk about the temperature, though, for a moment. Let me use this as an example. So, what?
Just before you go,
Okay.
Yeah, I want to just give a brief reminder. We have about 25 minutes left, so that might help you with pacing.
We have about 25. Why don't we take a break, don't you think?
Yeah, let's give it a couple minutes of break.
Yeah.
If you have questions, start, typing them in, and we will take them in. If you need to take a quick break, everybody, we all have some needs to attend to, so we'll be back in about a couple minutes. Not very long, but just take a quick break.
I'll be back for sure by 10 after, maybe even a minute or two earlier. But take 3, 4, or 5 minutes.
Just another quick update. If you are looking to get your CEUs, please email Allie Crampton with us over here at TDEC. I left her email in the chat box, so you can get her email from there.
Give me another minute or so, and then I'll start flapping my jaws again. How's that?
That sounds good. That brings us to about 20 minutes remaining until 11:30 Central Time.
Are we done at half past or quarter after or quarter of?
Mark's leaving at 11:30 today.
Oh, okay. All right. Let's see. Mark, you haven't gotten those other polling questions, so you can put those up and see which is the most popular ditch.
I wasn't the one who put them in, so I wasn't the one that was assembling them, but I didn't see it in there.
I'm not sure that we have that.
Oh, okay. Okay, maybe I didn't.
And I'm not leaving early, Karina.
Oh, you're not? What's
No.
Has to jump.
I may just leave 10 minutes early, but we can go with the full time whenever it's scheduled.
Oh, perfect. Yeah, that's great. Thank you, Mark. But I just want to make sure we fit it all in. Grant, I do not think that we had a poll on the different kinds of ditches. We had a poll on the different kinds of plants.
Okay, well, everyone, here we are. We're going to plod through this. There was a question about temperature.
Yeah, why is the phosphorus harder to remove in warmer temperatures?
Right. I have a theory, and it's the Grant Weaver theory. My theory is that in warm weather, if I were to go back into this diagram, and let's say we've got this nitrifying and denitrifying in the ditch so that we're converting ammonia to nitrate and nitrate to nitrogen gas. And we're using this zone as a zone for VFA production, and the phosphorus removing bacteria are consuming the VFAs in this zone. And as they do, they release phosphorus in a solution. So what I've seen, two things happen in warm weather. One thing that'll happen is this will continue working great. We're getting the phosphorus release. This is, if anything, maybe even works better in the summer, getting those first two steps done. Oh, I'm using my cursor as a marker. I'm sorry. Forgot. Let me bring the tool up. So what we're seeing is this is working well in the summer, getting the good phosphorus release. So one of two things can happen. This can still, the ditch is still doing a good job now. The aerobic condition, we've got the energized bacteria that are coming in here, they're sucking phosphorus out, they go into the clarifier, and doggone it, in the clarifier they start releasing phosphorus. That will happen more likely in the warm weather. I've seen for an oxidation ditch that's in Tennessee that the phosphorus releasing the ditch was very low, 0.0 something, 0.08. I think they were getting in the Athens Little Mouse Creek plant. Going into the clarifier and coming out of the clarifier was over 1. So if that happens during warm weather, that phosphorus that gets brought into the mixed liquor, it doesn't glom on that well, and it will release the phosphorus again pretty easily in warm water. So you got to go with an absolute minimum sludge blanket, a high rise rate, try to keep that sludge blanket to an absolute minimum. So that's one scenario that happens. Another scenario that happens is this is still working great. Everything's working in this end. The bacteria are energized. They're coming in here. And for some reason in this ditch, they just don't, the phosphorus doesn't get removed. The conditions are fine. You have the DO, the pH is fine, but it's not happening in the ditch. And at the other Athens plant, the Ustanala plant, this was a real problem for them in the warmer weather, and then an industry increased their organic production. I think it was a milk bottler or processing plant, and that dairy increased the load so that during the summer weather, now there's more VOD than there used to be. And my theory is, and it's a one-man theory, so take it with a grain of salt. My theory is that In warm weather, this zone is working so efficiently that there's almost no BOD coming in here. In fact, at Ustanala, they measured it, and they were seeing in the low teens BOD, soluble BOD coming in here. Just not enough for the bacteria that are energized to grow. So they're energized, they hit the oxygen, but there aren't the building blocks in there for them to grow, and since they don't grow, they're not sucking phosphorus out of solution. So if you see that problem, it's a fairly universal problem, and the tools are to look for any place that you get any kind of sludge settling after the aeration zone and eliminate it. Reduce your sludge blankets, and if that isn't it, and if you want to grab a sample and see if the BOD, soluble BOD is low, then you want to boost the BOD getting in here into the blue part, the aerobic part, so you can support that phosphorus removal. I'll use Great Bend as an example. It's a real nice example. There's going to be a write-up about this in the TPO magazine maybe next month or the month after. The folks there did exactly what we're talking about. They put a variable frequency drive on their rotor for their oxidation ditch so they could run that speed of that just right to get ammonia removal, which on this case is the bottom, the turbulent part that's going from left to right, and then the top part is anoxic, low enough oxygen. So took them several months to dial that in, get the right settings. There was a DO feedback so that is controlling the speed. So first they had to spend 25 grand or so to put in the variable drive on their motor. They already had the DO feedback loop, and then they controlled that so that mixer is running just enough to give them ammonia removal, but not so much that all that oxygen's moving throughout the ditch, and they have a nice zone for nitrate removal. Then they took, let's see what my little picture, that would be in that zone, and then in what was the anoxic zone is designed for nitrate removal. They don't need to remove nitrates, they're already being done in the ditch. So they turned that mixer off, which is right there and smack in the middle of that circle. There's a vertical shaft mixer. So they turned that off except for less than an hour a day. And that zone has become sufficiently anaerobic that they've got 2 or 3 months now of very good phosphorus removal out of a plant that really never was removing phosphorus. It's been a lot of fun working on that project. So, yeah, I didn't give credit to the people in Lansing, let alone Great Bend. So in Great Bend, we've got to give credit to Jason Cawley, Reuben Martin, April Batts in the lab, and this is James Gaunt here. Lansing, my other example is Tony Zell, Gordon Cunning, and Chris Bennett. My whole thing is it's the people that make the difference, and then I fail to acknowledge the people that make the difference. Shame on me. So here's the strategy they applied in Great Bend and are applying today. Is they're getting the nitrogen removal in the main body of the ditch, and they converted what was designed to be an anoxic zone. They converted it into an anaerobic zone. They closed that gate, turn the mixers off, and then gives them the phosphorus release, and then they're getting the uptake in the ditch. It will be very interesting to see how this works as it gets into warmer weather in Great Bend. All right, there's the break. We already had the break. You know what, I think I'm going to skip this one. This is pretty uncommon. So, even though I got these really cool rotors, let me show you my rotors. That was neat, I made this turn. All right, so everybody's impressed with that. We'll follow it, just dialing that in, and how we dialed that, they dialed that in, and we'll follow it. And that's Nick Cowan, which is pretty interesting because he's not Nick Willis of Cowan, who we've also worked with. This is Nick Cowan of La Follette, not to be confused with Nick Willis of Cowan and staff trying to reduce their chemicals. Techniques there was that 2 mixers in that ditch and they can manage their phosphorus removal that way. Maybe this will be of interest. Hopefully I'm picking the right one. So here's a ditch. This is the most common one I've seen, is an oxidation ditch that's designed with these are old style, right? These are early 70s, 80s ditches. They're designed basically for ammonia removal. They're not designed for total nitrogen removal. They're not designed for phosphorus removal. So how's a ditch like this designed to work, and how does it work? And then how can we get it to make, to achieve nitrogen and phosphorus removal? Well, the ditch is designed with, they're generally horizontal shaft rotors. It can be vertical rotors, as I had in some of the previous illustrations. But they're designed so however many aeration devices there are, that they run all the time. And the whole ditch is aerobic, has a healthy dissolved oxygen, and as such, these things do a fabulous job of removing ammonia. But there's no low oxygen zone for them to remove the nitrates that are created when you remove ammonia, so the total nitrogen is little affected in this technology. So if we want to make this thing into a nutrient removal, we want to optimize nutrient removal, so here's some tricks. So for nitrogen removal, I think you're probably guessing what we're going to do there. We're going to try to nitrify, convert the ammonia to nitrate, and denitrify, convert that nitrate to nitrogen gas in the main body of the ditch. And we're going to do that one of 2 ways, or maybe even a combination of the 2 ways. We're going to run with one of the 2 rotors so that we have a strongly aerobic side and a strongly anoxic side, and or we're going to cycle that one rotor on and off, or if we're running with both rotors, run both rotors on and off, so that instead of having spatially throughout the tank kind of a strong air zone and a low air zone, we're going to have the whole tank go strongly aerobic, and then the whole tank go strongly anoxic. 2 techniques to use. Just depends upon the conditions. Sometimes the tools that are available to the operators, like timers on the rotors. What can you accomplish? The simplest. For phosphorus removal, there's again 2 strategies. One is to actually purposefully create dead zones. Okay, I've advocated, with tongue in cheek, I've advocated throwing old wrecked cars into an oxidation ditch so that you've got a place in there that's just a dead zone, and all the sludge will settle inside. Take the windows out and throw the car in, and let the sludge settle in the driver's seat there. I'm kind of half serious about that. Maybe somebody will pick me up on that. But more seriously, if you turn both the rotors off for a period of time, some of the solids will settle to the bottom of the ditch, and in the bottom few inches of the ditch, or maybe even bottom foot, depending upon the depth of the ditch, if conditions are such that it allows that kind of settling, it can go anaerobic, septic enough to support phosphorus removal. And I've seen it more than once happen. So that's one approach. Pretty hard to dial that into a real low number, but it sure is a quick, cheap, and easy way. Okay. Totally counter to everything we've learned. We're allowing settling to occur in our ditch, and we're benefiting from it. The second way is to take some of the sludge, some of the return sludge or waste sludge, run it through septic conditions sufficient to create the volatile fatty acids, interact with the bacteria in either the RADs or the waste activated, and then return that energized sludge into the ditch. That's a more controllable method, more likely to have consistent, reliable success. Any questions or comments? I'll pause. If not,
I've got one in the Q&A.
okay.
If we want to recycle some flow from the inside of our orbital ditch to the outside ring to achieve nitrate removal, how much flow would we recycle? Also, what's the best method for that? Pump style, etc.
All right. The orbital would be the next next example I want to go through. So if we have time, we'll do that. If not, I think we'll put that at the front of our next presentation. So if we can hold off on answering that when we're doing the orbital, I would like to do so. Is there anything else? Because it's a good question.
No, nothing else.
All right, let me talk about Harriman. Here's a plant. I had the pleasure of working with Ray Freeman, and I got to give a shout out to Dwayne Culpepper of TAUD. It's been fantastic working with those two. There's Ray on the left, and I'm the old geezer that looks like he's about to pass out, wearing the stupid hat and shirt on the right there. So Harriman is a treatment plant, oxidation ditch, not designed for nitrogen removal, not designed for phosphorus removal, run by this long-haired guy over here. And look at the numbers. Oh, John West definitely gets credit here. John West of TDEC really got this effort started. So several years ago, okay, so let's look at the numbers. Effluent nitrogen historically was over 20, now it's 1/10 of that, 2. Phosphorus historically around, call it 3, of late, half that. Okay, so that's, I don't know where you come from, but from where I come from, that's pretty good. A facility not designed for nitrogen removal is in 2.3, which very few facilities designed for nitrogen yet. And phosphorus, okay, it's over 1, but they cut it in half. Ray, through his creativity and staff, and through the good guidance of John got him started, John West of TDEC, and then a lot of support from Dwayne Culpepper. And then I've had the good fortune to come along and watch their good work. So what happened here? So Harriman, as designed, has 4 rotors designed for all of them to run. So even before Ray started working there, John West stopped by and talked to the staff and said, hey, maybe you don't need to run all 4 of those all the time. Why don't you try running with less than 4 all the time? So they began cutting the rotors out. And then along comes Ray, and after a few years of effort, Ray now is running 1 rotor in 1 ditch for a while, and then no rotor. And then the other rotor in the other ditch, and then no. So we've gone from 4 running all the time to 1 of the 4 running a minority of the time. Huge electrical savings, right? The biggest electrical use in most treatment plants is aeration, and they've cut the aeration by more than 75% in Harriman. There used to be 4 running all the time, now we're running with less than 1 on average. I don't know what those are supposed to mean. So now, once a day, both of the rotors in one basin and then both the rotors in the other basin will come on and resuspend the materials. So by running 1 rotor on long enough for ammonia removal, okay, process control, measuring the ammonia, seeing if I've got enough aeration for ammonia removal. Once I do, I don't need any more aeration. Okay, the plant's underloaded. They're running below design capacity, so they have surplus capacity. So he has the ability to do this. So he runs it long enough to get the ammonia conversion to nitrate, and turns them off long enough for nitrate conversion to nitrogen gas. As they're off, they're settling. As they're settling, he creates that septic zone. And then once a day, he not only turns 2 on to resuspend, like shown in this picture, but recently started running those 2 for a little longer, maybe for an hour and a half or 2 hours. And he's doing that in an effort to really boost the dissolved oxygen in there to see if that will help foster the phosphorus uptake. And it seems to have helped. So there's a great example of a facility that's going 3-dimensional with the phosphorus and cycling on and off like a sequencing batch reactor. Cookeville is our all-star facility. It was featured in the December TPO magazine. That picture was taken from the magazine, and there's the cover of the magazine. So a lot of people here to thank, and Karina gets a lot of credit for getting this whole thing on its way. But in the middle there is Tom Graham, who's the superintendent, and the tall guy to the left of him with the goatee is John Buford. Those 2 were really the team folks that really got it going, and of course with the support of their utility manager, Ron and Kelly. There's the nitrogen before and after. They dialed it in, so it dropped from 15 to less than 5, or they're bouncing around 5. Phosphorus not a real dramatic drop, but improving, right? They're getting more control of their phosphorus, and phosphorus often takes time. You can see their effort began like in 2015, so phosphorus did take a nice drop there in 2015, and then something happened in 2019, kind of climbed back up. Seems like it's working its way back down again. What happened in Cookeville? Well, same story. The plants, I'm going to talk about one of the 4 ditches, but you can see there are 4 of these oxidation ditches. Each ditch has 6. Well, let's say there's 4 ditches. Each one has 6 rotors. So the plant as designed had 24 rotors running 24 hours a day. So these guys started experimenting with it, these guys being Tom and John. So let's just use one of the ditches as our illustration. Same thing happened in all 4 ditches. So they now run with 2 rotors for a period of 4 hours. Okay, 2 rotors at each of the 4 ditches. So that creates a strongly aerobic zone immediately downstream of those rotors. It creates kind of a dead zone in advance of those rotors. And in between, a strongly anoxic zone. And then 2 more rotors for the next 4 hours. Now this sludge blanket, so they believe, and I believe with them, kind of moves around the bottom with all of this. In the next 4 hours, 2 in a row to create a strongly aerobic zone. So every 12 hours, we just went through 12 hours, and the next 12 hours we start all over again with the first 2 up at the top. So that's created a major improvement in nitrogen removal, and improvement in phosphorus removal, and reduction in their electric bill of $250,000 a year, which I'm sure went immediately to raises to Tom and John, if only. They deserved it. All right, in the time that remains, and I don't know, Karina, we're done. It's 12:30. Should I end, or should I do Orbital now or next week?
Let's do Orbital now.
Okay, we're going to do Orbital now. So there was a question about increasing the recycle rate from the middle. So I may need to have you ask that again, but not right now. Let me go through it, and then we'll get to that question. I've seen these things run in different ways. Generally, the idea is the outer ring is for anoxic. So it's for low oxygen. It gets the internal recycle coming from the middle ring back to the outer ring, and the influent is going into the outer ring. So it's designed typically for nitrogen removal. I've seen cases where it's designed to go totally anaerobic for phosphorus removal. So let's go with the design where it's not designed for phosphorus removal. So the flow comes in, goes around the outer ring. The outer ring in one of these, if it's a 3-ring orbital ditch, contains half the volume of the entire ditch. So half the volume now is anoxic. It's getting the return sludge and the influent and just enough oxygen to keep it from going too septic. The middle ring, the flow moves into the middle ring and then also goes around that ring. As it does, there's a little more oxygen and enough to get some ammonia removal, but not so much that it can overwhelm, that it has a real high dissolved oxygen. And then typically the innermost ring has a high dissolved oxygen, and look at all those arrows, huh? What a mess. And as it goes around the middle ring, the ammonia is converted to nitrate, and then there's an internal recycle that pumps that flow to the outer ring so that the ammonia that got converted to nitrate, those nitrates get pumped to the outer ring, they mix with the influent in a low oxygen zone for total nitrogen removal. Hopefully that makes sense. Oh, and then of course, some of the flow moves out of there and goes to the clarifier. So this is a technology that's designed for nitrogen removal, often sometimes for phosphorus removal too. If it's designed for phosphorus removal, the internal recycle does not occur. It's not recycling back to the outer ring. The outer ring is being driven septic for the VFA production and the VFA uptake by the bacteria in the return sludge. So that arrow, if it was designed for phosphorus removal, it would not pump to that zone. So you want to measure and monitor what's going on in those zones, those aerobic and anoxic zones. And for phosphorus removal, what they found in Athens Ustinala was it got terrible phosphorus removal in the summer. There was so little BOD getting into that inner ring that it's hard to imagine that there was enough to support the growth of bacteria. So bacteria weren't growing, so since they weren't growing, they weren't sucking phosphorus out. So what they did in the case of Ustinala is they created a side chain fermenter, which I can talk about in just a moment, but if one of you, the panelists here, can refresh my memory, what was the question that it blew off that came earlier?
He said, if we want to recycle some flow from the inside of our orbital ditch to the outside ring to achieve nitrate removal, how much flow would we recycle? Also, what's the best method for that, pump style, etc.?
Okay. All right. That's a very good question. And all right. So, I mean, so how much do you pump? That's the question. How much do I pump here? Okay. There's two determining things. If you pump too much, this outer ring starts to get too high a dissolved oxygen. I tell you what, that's pretty unlikely. It's a massive amount of zone. But it's possible. So if you pump too much, this zone will become, the outer ring will get polluted with the dissolved oxygen coming from that inner ring. And if it does, then it's no longer going to remove nitrates. So let's get my little marker tool here, which I know kind of mucks up the picture, but so if we're pumping too much here, the dissolved oxygen in this zone is getting too high, and if there's a way to grab a sample as it goes into this zone, then you'll see a lot of nitrates going into this zone. That means the pumping rate's too high. If the pumping rate is too low, then this outer ring has the capability, the appetite, if you will, to take in more nitrates if only you'd send them here. Okay, what's the downside of that? Well, what's coming out of here now into this zone is almost has no nitrates in it. So if you would increase this, then you'd be sending more nitrates to get removed. And you'd want to, if there's no nitrates coming in here, by definition, this pump rate can be increased. If there are nitrates coming in here, then it's a dance. How much more you can bring into this zone without polluting it, and how little you can send in here without getting an elevated nitrate in your effluent. Because after all, it isn't how much coming through this wall that you want to maximize, it's how much going to the final clarifier that you want to maximize. I don't know if that was confusing or helpful. I don't know why I got that. So try to close those tools out and see. There we go. So it's that one that we want to minimize. Does that help with the question? Or if there's any more to that question, please type it in while I run through this case study, and then we'll wrap this thing up. So here's the Ustanola plant. You can see in the top has the two orbals. Just a little quickie schematic showing how the flow moves through the plant. So what was done here was to maximize phosphorus removal, they set up a side stream fermenter using some old plant equipment. They took a clarifier, they built a little pumping station beside it, they figured out an elevation in that old clarifier that was the perfect elevation that if they sent about 10% of their waste flow into there, that it would sit for 2 to 7 days and ferment. And as it fermented, create volatile fatty acids. As the volatile fatty acids were created, the waste or RAS that went into that would consume the volatile fatty acids. They become energized, and then through that pumping station would be sent back into the orbital ditch. Now, what I particularly, of many things I like about working with Athens and working with Greg Hayes, Russell Coleman at this plant, and John Sullivan at North Mass Creek, they were believers, early believers and risk takers. So Ustanola is a member of AMSA, I think it is, one of the trade associations, and for years they've been getting awards for having perfect compliance records. They were adding chemicals to get phosphorus removal. And they knew that if they stopped adding chemicals, they were at risk of losing their award because they would have to learn how to bring the plant into control without chemicals. But with the support of TDEC, and Karina again gets a lot of credit for this, and all the way up to the top of TDEC, Jenny, Dab, and the entire team there, they encouraged them. They said, we'd rather you learn to not use chemicals, do it biologically. That's better for the environment. So we're going to be with you while you transition. So sure enough, they did. And even though I'm showing some spikes up there, it's continued to phosphorus number. And today's presentation, lots of people to acknowledge. It's just unbelievable, the people that I've met over the years and are applying themselves to create these great results. Take the credit for it, but all of these folks are the ones that made it happen. So next week we're going to do SBRs. We'll get our polling questions together. That's on me, and I apologize for that. And then afterwards, we're going to be doing conventional and anyone who's interested in let's talk about their plant, let us know. And one way you can write that. Anything else anybody in the team wants to say or comment?
Should I open the final poll?
Yeah, go for it, Mark.
Alrighty, I'll do that. Alright. Ended up and I hear is being expert and one being new to the topic. Host mode to you. Alright, looks like they're all done. I'm going to close out this poll. Okay, I'm going to hand over the host capabilities to Allie. I did not save the poll, so you might want to do that before we get off.
Thanks, Mark.
I appreciate the recording. Really into and going into the details of each design of an oxidation bid, so it was very helpful. I know we did not answer all the questions, and I'm sure you didn't wanted to ask. So, and we are all on the journey.